At the 9 o'clock meeting this morning, I didn't remember to start the YouTube to go along with the Zoom meeting. So I am creating this video in case you need to watch the part 1 of chapter 7, section 3 on trigonometric substitution. Hey, in section 7.3, we talk about another change of variables. We reviewed the substitution rule, which is a change of variables. When applying the substitution rule, the new variable is a function of the original variable. This is the equation that we use for the substitution rule. We have the indefinite integral of f of g of x times g prime of x dx. And that is written in a simpler form, the indefinite integral of f of u du, where u is equal to g of x. In this section, chapter 7, section 3, we are going to discuss trigonometric substitution. And this is the inverse of the substitution rule. With trigonometric substitution, the original variable is a one-to-one function of the new variable. So if we start out with the indefinite integral of f of x dx, we transform that into the indefinite integral of f of g of theta times g prime of theta d theta, where x is equal to g of theta, which is a one-to-one function. It's necessary that x equals g of theta be one-to-one so that the change of variables can be reversed to express the evaluated integral in terms of the original variable. The trigonometric substitution is done so that we will get an indefinite integral that is easier to evaluate than the original indefinite integral. So we'll review a little bit about restricted domains for sine, tangent, and secant. You'll recall that in order to define inverse sine, inverse tangent, and inverse secant, sine, tangent, and secant have to be defined on restricted domains so that they are one-to-one on those domains. So here, if we have x equals sine of theta, so theta is the domain variable and x is the range variable. To make the sine function one-to-one, we restrict the domain to the interval from negative pi over 2 to pi over 2. So if we sketch a graph of that, the horizontal axis is the theta axis, the vertical axis is the x-axis in this case, and the maximum value of sine is 1, the minimum value is -1, and on the interval from negative pi over 2 to pi over 2, the graph of the sine function looks sort of like this. So as you can see, if we restrict the domain of sine from negative pi over 2 to pi over 2, it is a one-to-one function on that interval. For x equals tangent of theta, we restrict the domain to be strictly between negative pi over 2 and pi over 2. And remember that for the tangent function, negative pi over 2, I should say theta equals negative pi over 2 and theta equals pi over 2 are vertical asymptotes for the graph of the tangent function. And in between negative pi over 2 and pi over 2, the graph of the tangent function looks sort of like this. It passes the horizontal line test, and so it is a one-to-one function. For x equals secant of theta, We have two cases to consider. Well, when secant of theta is positive, the restricted domain is from 0 to pi over 2, where we include 0 but exclude pi over 2. So we'll draw a little graph of that. So the interval from 0 to pi over 2. And for the secant function, so theta equals pi over 2 is a vertical asymptote. Secant of 0 is 1. And so on this restricted domain from 0 to pi over 2, x equals secant of theta, the graph looks something like this. And it passes the horizontal line test, so it's a one-to-one function on that restricted domain. Well, it's also possible that secant of theta could be negative, just as sine of theta is negative and tangent of theta is negative. But in this case, we restrict the domain to be from pi over 2 to pi, excluding pi over 2. So this time, we plot the points pi over 2 and pi on the theta axis. Theta equals pi over 2 is a vertical asymptote. And between pi over 2 up to pi, including pi, secant is negative. Secant of pi is negative 1. And then the rest of the graph looks something like this. Okay, the primary trig functions that we use with, or use for trig substitution, are sine of theta, tangent of theta, and secant of theta. Okay, in the next page, we have some expressions and some substitutions that go with those expressions. So if we see an expression like this, the square root of a squared minus x squared, and if we find that this is in the integrand of an integral, we can generally find a simpler integral to evaluate if we use this substitution, x equals a times sine of theta. The related identity is 1 minus sine of theta squared equals cosine of theta squared. So if we replace x with a times sine of theta, then we're going to get the square root of a squared minus a squared times sine of theta squared. And then if we factor out a squared from the two terms, we have the square root of a squared times the quantity 1 minus sine of theta squared. And then we use the identity over here. 1 minus sine of theta squared equals cosine of theta squared. And we get the square root of a squared times cosine of theta squared. And the square root of that is a times cosine of theta. And since cosine of theta is positive, well, it's greater than or equal to 0 on the interval from negative pi over 2 to pi over 2, we don't need the absolute value symbols to surround cosine of theta. So you'll agree, perhaps, that when you compare a times cosine of theta with the square root of a squared minus x squared, a times cosine of theta is a much simpler, well, it's simpler at least, than the square root of a squared minus x squared. So that's the purpose for using that substitution, is to make expressions simpler. Hey, in the next one, if we see something like this, an expression with the square root of a squared plus x squared, then we want to use x equals a times tangent of theta. The related identity is 1 plus tangent of theta squared equals secant of theta squared. So if in this expression we replace x with a times tangent of theta, we're going to get the square root of a squared plus a squared times tangent of theta squared. We'll factor out the a squared, so we get the square root of a squared times the quantity 1 plus tangent of theta squared. And then we use this identity over here, 1 plus tangent of theta squared equals secant of theta squared. So we write this as the square root of a squared times secant of theta squared. And then the square root of a squared times secant of theta squared is a times secant of theta. So once again, by making that substitution, we end up with a times secant of theta, which appears to be simpler than the expression, the square root of a squared plus x squared. Also on the interval from negative pi over 2 to pi over 2, secant of theta is positive, so we don't need the absolute value symbols around secant of theta when we take the square root. Okay, a third area, or a third place where we use trig substitution. If we have the square root of x squared minus a squared, we use x equals a times secant of theta. The related identity is secant of theta squared minus 1 equals tangent of theta squared. Okay, so if we replace x with a times secant of theta, we're going to get the square root of a squared times secant of theta squared minus a squared. Inside the square root, we'll factor out a squared, so we get the square root of a squared times secant of theta squared minus 1. And then we use the identity. We're going to replace secant of theta squared minus 1 with tangent of theta squared. And so the square root of a squared times tangent of theta squared is a times tangent of theta. And on this domain from 0 to pi over 2, tangent of theta is positive. Okay, this fourth substitution it's just the same substitution, just on a different domain. So we'll bypass this one for now, since the substitution is the same. Now let's look at some examples involving trigonometric substitution. Okay, in our first example, we have the indefinite integral of x to the third over x to the over the square root of x squared plus 4 dx. So this form, the square root of x squared plus 4, we pick x to be 2 times tangent of theta. And so dx will be 2 times secant of theta squared d theta. And we're going to replace x with 2 times tangent of theta, and we'll replace dx with 2 times secant of theta squared d theta. Okay, so our indefinite integral, we're going to raise x equals 2 times tangent of theta to the 3rd power in the numerator. In the denominator, we have the square root of x squared, which is 4 times tangent of theta squared plus 4. And then we remember dx is 2 times secant of theta squared d theta. And now we'll do some arithmetic in the numerator of the integrand. We're cubing 2 times tangent of theta, so 2 to the 3rd is 8. Tangent of theta cubed is tangent of theta cubed. And I'll go ahead and write what dx is in the numerator, since that belongs in the numerator. So times 2 times secant of theta squared d theta. And then in the denominator, well, we saw on the previous page how to simplify something like this. The square root of 4 times tangent of theta squared plus 4 is equivalent to the square root of 2 times secant of theta squared. And the square root of 4 times secant of theta squared is 2 times secant of theta. So I didn't include all of the details, but the square root of 4 times tangent of theta squared plus 4, after we make this the substitution, it's going to simplify to 2 times secant of theta. Okay, so we can simplify the constant factors. In the numerator, 8 times 2 is 16, divided by 2 is 8. So I'll bring the factor 8 out front of the indefinite integral. We're going to get 1 factor of secant of theta to cancel. So we'll write this as tangent of theta cubed times secant of theta d theta. Okay, so what I'm going to do next, I'm going to take one of the factors of tangent of theta and put it alongside secant of theta. So we get 8 times the indefinite integral of tangent of theta squared. And then I'm going to write the remaining factors as secant of theta times tangent of theta d theta. Then I'm going to use an identity and replace tangent of theta squared. So here we have 8 times the indefinite integral. Replace tangent of theta squared with secant of theta squared minus 1. And then this is times secant of theta times tangent of theta d theta. All right, we know that secant of theta times tangent of theta is the derivative of secant of theta. So I'm going to apply the substitution rule. So we started out with a trigonometric substitution, and now I'm going to use the substitution rule, where u is secant of theta, And du is secant of theta times tangent of theta d theta. Okay, so when we make our substitutions, we get 8 times the indefinite integral of u to the second minus 1, and that quantity is multiplied by du. So this is a simple integral to evaluate. So we have 8 times u to the second over, u to the third over 3 minus u plus a constant. And now we're going to replace u back with secant of theta. So I'll just write this as 8/3 times secant of theta to the third minus, instead of minus 8 times u, I'm going to write minus 8 times secant of theta and then plus a constant. Well, we're still not done because the original integrand is in terms of x. So now we have to find something to replace secant of theta with that's written in terms of x. We use our original assignment, x equals 2 times tangent of theta, to help us do the rest. So we picked the substitution x equals 2 times tangent of theta, and that means tangent of theta is equal to x over 2. Okay, so we use right triangle trigonometry to help us. So I'll draw a right triangle right here, and I'll label this angle theta, and if tangent of theta is x over 2, the length of the opposite side to theta is x, and the length of the adjacent side is 2. And then using the Pythagorean theorem, we can find the hypotenuse, the length of the hypotenuse is the square root of x squared plus 4. Okay, so we want to know what secant of theta is. We know that cosine of theta is adjacent over a hypotenuse, and secant is the reciprocal of cosine. So secant of theta is the square root of x squared plus 4 over 2. Okay, so the answer to our indefinite integral then is 8/3 times secant of theta to the third, so I'll just put the square root of x squared plus 4 over 2 to the third, and then minus 8 times secant of theta, so 8 times the square root of x squared plus 4 over 2, and then plus a constant. We can simplify a little bit more. So when we raise this expression to the third power, we're going to get 8 in the denominator, and 8 divided by 8 is 1. So this is going to be 1/3. And then we know that the square root of x squared plus 4 is the same as the quantity x squared plus 4 to the 1/2. So when we raise that to the third power, we'll get the quantity x squared plus 4 to the 3/2. And then we simplify this one, common factor of 2 cancels, so we get minus 4 times the square root of x squared plus 4, and then plus a constant. Okay, so that completes that integral. Let's take a look at the next one. The indefinite integral of the square root of x squared minus 1 divided by x to the 4th. Okay, so on this one, since we see the square root of x squared minus 1, we'll pick the substitution for x. X equals 1 times secant of theta, or just x equals secant of theta. And so dx is secant of theta times tangent of theta d theta. Okay, so we replace every x with secant of theta. And then we remember that dx, what dx is. So we get the indefinite integral. In the numerator, we have the square root of secant of theta squared minus 1. And then in the denominator, we are raising x to the 4th power. So we get secant of theta to the 4th power. And then we multiply by dx, which is secant of theta times tangent of theta times d theta. Okay. So we know that secant of theta squared minus 1 is tangent of theta squared, and the square root of tangent of theta squared is just tangent of theta. So in the numerator here, we'll just replace that with tangent of theta. We're going to get a cancellation, secant of theta in the numerator with one of the factors of secant of theta in the denominator. So I'll just write that as the result of that is secant of theta to the 3rd in the denominator. And then we're just multiplying by tangent of theta d theta. Okay, tangent of theta times tangent of theta is tangent of theta squared. So I'll write the indefinite integral of tangent of theta squared in the numerator and secant of theta to the 3rd in the denominator d theta. Sometimes you'll see the advice or the procedure that when possible, write everything in terms of sine and cosine. And we can do that here because we know that tangent of theta is sine of theta divided by cosine of theta. And we know that secant of theta is 1 over cosine of theta. So I'll do an intermediate step here. I'll write the indefinite integral of tangent theta squared. And since we have, in effect, we have 1 over secant of theta to the 3rd, that's equivalent to cosine of theta to the 3rd in the numerator. Then we'll rewrite tangent of theta squared in the integrand as sine of theta squared over cosine of theta squared multiplied by cosine of theta to the 3rd d theta. And cosine of theta to the 3rd divided by cosine of theta squared is just cosine of theta in the numerator. So this becomes the indefinite integral of sine of theta squared times cosine of theta d theta. Okay, we can use the substitution rule again, which is the inverse of the trigonometric substitution that we started with. If we pick u to be sine of theta, then du is cosine theta d theta. So we can transform that integral to the indefinite integral of u to the 2nd du. And the indefinite integral of u to the second du is 1/3 times u to the third plus a constant. And then we replace u with sine of theta again, and we get 1/3 times sine of theta to the third plus a constant. Or, yeah, what did I write? 3. That's a constant, but plus c. Hey, now we have to make one more substitution. We have to replace sine of theta with an expression that's in terms of x. Okay, that's where the assignment x equals secant of theta comes into play. So this was our original substitution, x equals secant of theta. We use right triangle trigonometry to help us again. So sketch the right triangle. This is my angle theta. And if secant of theta is x, or x over 1, and it's the reciprocal of cosine, I have to have x is the length of the hypotenuse, the adjacent side is 1. And then using the Pythagorean theorem, we can find that the vertical side, or the side opposite the angle theta, is the square root of x squared minus 1. And we want to know what sine of theta is, so because that's in the answer to the indefinite integral, sine of theta is the square root of x squared minus 1 over x, opposite over hypotenuse. Okay, so I'll rewrite the original integral here. The original indefinite integral of the square root of x squared minus 1 over x to the 4th dx is just, well, we have to cube this. We have to multiply 1/3 times sine of theta cubed, which is the square root of x squared minus 1 over x raised to the 3rd power plus a constant. And we might as well simplify it a little bit more. So I'm going to have 1/3 x squared minus, the square root of x squared minus 1 is x squared minus 1 to the 1/2. And when I raise that to the 3rd power, I'll get x squared minus 1 to the 3/2. And then in the denominator, x is raised to the 3rd, so I get x to the 3rd in the denominator. And that's a pretty good answer for that one. Okay, we'll look at just one more integral involving a trig substitution. I'll only go as far in this video as how far we went in class today, so just one more to do right now. Okay, this one, the indefinite integral of x squared over the square root of 4 minus x squared dx. Okay, so when it's in this form, we're going to pick x to be 2 times sine of theta, and dx is 2 times cosine of theta d theta. And then we substitute into the indefinite integral. So the indefinite integral, in the numerator, we're squaring 2 times sine of theta, so we're going to get 4 times sine of theta squared. And in the denominator, the square root of 4 minus x squared, that becomes the square root of 4 minus 4 times sine of theta squared. And don't forget dx. Dx is 2 times cosine of theta d theta. Okay, in the numerator we'll just keep the 4 times sine of theta squared there. I guess we can take a little time to simplify the square root of 4 minus 4 times sine of theta squared. So factor 4 out of the terms inside the square root. So the square root of 4 times the quantity 1 minus sine of theta squared times 2 times cosine of theta d theta. We're going to replace 1 minus sine of theta squared with cosine of theta squared. So we get the indefinite integral of 4 times sine of theta squared. Okay, square root of 4 times cosine of theta squared times 2 times cosine of theta d theta. And then we get, in the numerator, 4 times sine of theta squared. And then the square root of 4 times cosine of theta squared is 2 times cosine of theta times 2 times cosine of theta d theta. So we get a nice cancellation here. 2 times cosine of theta divided by 2 times cosine of theta equals 1. So now I'll bring the factor 4 out front, so it's 4 times the indefinite integral of sine of theta squared d theta. Remember that sine of theta squared is 1/2 times the quantity 1 minus cosine of 2 theta. That's the reduction formula for sine of theta squared. So we'll write this as 4 times the indefinite integral of 1/2 times the quantity 1 minus cosine of 2 theta d theta. Let's multiply 4 times 1/2 and bring the factor 2 out front. So we get 2 times the indefinite integral of 1 minus cosine of 2 theta d theta. And now we can find the antiderivative. So this is equal to 2 times theta minus 1/2 sine of 2 theta. Plus a constant. Let's just leave the plus c until later. So this is equal to 2 times theta minus 1/2 times, and then sine of 2 theta, a nice identity for that is 2 times sine of theta times cosine theta. So 1/2 times 2 is 1. So let's write this as 2 theta minus 2 times sine theta cosine theta. Okay, then there's a plus a constant. Okay, but now we have to replace sine of theta with the appropriate expression in terms of x, the same with cosine of theta, and also we have to replace theta. Okay, the original substitution for this problem is x equals 2 times sine theta. So that means x divided by 2 is sine theta. Okay, so that's going to go in a couple of, well, just one place. over here, we're going to replace this sine of theta with x over 2. And we're going to replace theta with, well, if sine of theta is equal to x divided by 2, then that means theta is equal to the inverse sine of x over 2. So we're going to replace theta with the inverse sine of x over 2. And now all we have left is to determine what cosine of theta is. So we'll use a right triangle to help us on this one. Right triangle with the angle theta, and sine of theta is x over 2. So the opposite side of theta is x, the hypotenuse is 2. And then using the Pythagorean theorem, we can find that the length of the adjacent side is the square root of 4 minus x squared. And so the cosine of theta is the square root of 4 minus x squared over 2. Okay, so I'll squeeze in here in this little red box, kind of like a box, the result. The original indefinite integral of x squared over the square root of 4 minus x squared dx. So that's equal to 2 times theta, but theta is inverse sine of x over 2. So this is 2 times the inverse sine of x over 2 minus 2 times sine of theta, but sine of theta is x over 2. So 2 times x over 2, that could be simplified. And then cosine of theta, we found that to be the square root of 4 minus x squared over 2, and then plus a constant. Okay, I ran out of space. This can be simplified a little bit more. Those two's cancel, but that's a pretty good answer. Okay, so that's as far as we got in class this morning. So that's where I will stop right now. And on Monday, see, what's the date on Monday? The 24th. We'll do the rest of the problems from Chapter 7, Section 3.